All right, what we're going to look at in this video is the change of base formula with logarithms. So the change of base formula with logarithms came when back many years ago when there was just slide rules and people could not calculate anything other than base 10. So we needed to change the base into that common base of 10, and so we could calculate it using our slide rules. But we don't have slide rules anymore. But unfortunately, some of our calculators still do not allow us to calculate these things outside of base 10. So let's say we've got this general logarithmic formula. Log base b of a equals x. And we could write that again as a equals base b of x. This is just using our basic identity property with logarithms. So we could take a log to both sides of our equation. So looking over here at the right, we've got log. Let's just say we're going to change it to base c. I have no idea what base c is, but we know that we could take the log of base c to both sides, and it'll still remain an equivalent statement. We go through and simplify a little bit further using our exponential or our logarithmic rules. We move that x over to the front here. Right? So now we want to solve for x. We want to get x by itself. So we're going to divide the whole thing by log of c of b, log base c of b, log base c of b. And we know that we have to consider these things as an entire chunk. We can't just get rid of a b. We can't just get rid of the log. We have to look at the whole chunk. And since we've got x times log base c of b divided by log c base c of b, we know that those can cancel out. We're left with just log of base c of a over log of base c of b, and that's equal to our x. So we know that we've got this equivalent statement. This thing is the same as what we had up above. Let's undo that. So we've got, it's not cutting right in the middle there. Let's get that out of there. And so we're going to change this, and we're going to have that nice and neat. So we've got log, that thing is equivalent to what we had up above of log of base b of a equaling x. These two things are the same. So that's going to come in handy here in a minute as we start changing and looking at different logs and how we can switch these things around. So let's start with our first one. Let's say we want to simplify this. We want to simplify the statement log of 16, log base 16 of 32. All right, so using the same idea up above, if we've got something like this, log base b of a, log base b of a, yes. And we could change it to a different base over here on the right, log base c of a over log base c of b. What base should we change it to? Well, if we look at this, you might recognize that there's a common base between these two. You might recognize already that they both can be 16 can be found through powers of 2. 32 can be found through powers of 2. So let's use that. Let's take this and change it to the base of 2. So if we just look to see where things changed up above in the blue, log of base b of a, we ended up with the new base and the a up in the numerator. So we've got the log of the new base of the a in the numerator, and we've got the log of the old base, or log of the new base, the old base in the denominator. See how those matched up? So we've got this b and the b down here. We've got this a, we've got the a up at the top. So that's all that we did down here. We've got this b down here, matching up down below, and this 32 matching up right here. So, great. We're still trying to simplify this though. So how do these things simplify? Well, we know that 32 is 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And that we just also found out that 16 is 2 to the 4th. Okay, using our exponential or our logarithmic rules again, we know that 5 log base 2 of 2 over 4 log base 2 of 2. You can look at this in two ways. The log base 2 of 2 can cancel out to be 1, or you've got the same thing in the numerator and the denominator, and you're left with 5/4 for your solution. All right, so that's what you can do if you recognize that they have the same base, if the 16 and 32 or numbers like that have the same base. But they're not all going to have the same base. So let's take a look at one that might be a little different. Actually, we'll do it over here on the right, so that way we can keep that up there. So let's say we've got, try something new. Let's say we've got log, again, new column here, log of base 2 of 3. All right, in this instance, we don't have, these are both prime numbers. There's no common base between these. So let's just use base 10. So following again the same pattern. The 3 stays in the numerator, the 2 goes in the denominator, right? So log of base 10 of 3, which stays in the numerator, log of base 10 of 2 stays in the denominator. And what do we do now? Well, we can't simplify much further other than going to our calculator. So if we go to our calculator over here, so let's take a look. So we've got log of base, nope. Let's see, we've got our calculator, so we've got log, second log, and now my calculator allows me to do base 10, but I'm just going to say, we'll just put it in there, or I can change my bases and do the formulas in mine. Not everybody's can do this though. So we said it was log of base 3 on the numerator, log of base 3 in the numerator, or log of base 10 of 3 in the numerator, and we wanted to divide that by, so divided by log of base 10 of 2. And we get, ta-da, 1.58496. So we'll just use this, we'll do equals 1.585. Great. That's all there is to it? Yeah, that's all there is to it. And let's just double check. Let's just double check to make sure that this is actually the case. So if this were the case, then we would say that log of base 2 of 3 equals 1.585. That's what we're saying. 1.585. So how do we solve this? Well, let's just take it out of our logarithmic form. So that should say that 2 of 2 to the 1.585 power should be approximately 3. Now I'm saying approximately because I did some rounding. So let's check with our calculator again and see how we do, just to make sure that this thing is almost 3. So we're going to take 2, I'm going to raise it to the power of 1.585, and I should get close to 3. Look at that, almost, or a little over 3. So we do see that that is the case. So that's how that could work with your calculator. Now let's look at one just a little bit more complicated, something that you might have to do a little bit of work to first, and see how that one works out. So it's not going to be just a straight simplification problem like that. So let's look at 8 to the x power minus 5 times 4 to the x power equals 0. All right, well, this clearly is a little bit more complicated. If we want to find out what x is, that's going to be kind of hard to do. So we're going to first start by trying to do some factoring, doing some rearranging, and then we'll get to our logs and our change of base. So you should recognize that with your 8 and your 4, again, we've got a common base of 2. So we're going to rewrite this. 2 to the x power, and which power are we going to? 2 times 2 is 4 times 2 is 3 power, and then we've got 5 times 2 to the x power squared, and that all equals 0. Now I could have put 2 cubed to the x power, and I could have put 2 squared to the x power, but using my laws of exponents, I know that I can swap those around. It doesn't really matter which way I go, so I did it this way to save myself a step. All right, so we have 2 let's see, 2 to the x, so we can factor out. Let's see what happens when we factor out a 2 to the x power. Let's see, we've got, is that what we want to do? I think that's what we want to do. So we have, factor out a 2 to the x squared. Because that's the most that I can pull out from over here, right? That's the most I can pull out is 2 to the x squared. So I'm left with, inside my brackets, 2 to the x power minus 5. We might want to do a square bracket since that's what I've got on this other side. And that all equals 0. Okay, well, that's not helping a whole lot yet. But let's see. 2 to the x power minus 0, I'm sorry, 2 to the x to the squared and times 2 to the x minus 5. So this takes us back to quadratics. So in quadratics we said if this thing, if that equaled 0, then this whole side would equal 0, right? And if this over here equaled 0, then it wouldn't matter what I had for 2 to the x squared, because if I'm taking that times this green 0, then the whole thing is going to be 0. So what we're going to do is we're going to set both of these things equal to 0 and see what we can find. So we've got 2 to the 2x power equals 0. All right, so let's see. So if we do this with our base 2 logarithms, then we would have log of 2 to the 2 to the 2x power equals log of 2 to the 0 power, right? And we know that this is going to cancel out here on the left. That's going to cancel out, so we're left with 2x equaling log of base 2 of 0. Well, if we punch this into our calculator, you're going to see that you have a problem. And the problem is this 0. We haven't talked about this much, but you cannot have a logarithm less than or equal to 0. So this does not work. You can't do this. Does not work. NA does not work. Can't happen. So this one is invalid, so we can't solve for that one. But we can solve for the other side. We can solve for the 2 to the x minus 5. 2 to the x minus 5 equals 0. And what are we going to do with that? We're going to add 5 to both sides, and we're left with 2 to the x equals 5. Let's take our base 2, or our log of base 2 again. Log of 2, going to fit, yep. So this cancels out, and I'm left with x equaling log of base 2 of 5. All right, well, we saw in my calculator I can calculate that, but in your calculator you might not be able to. So let's change the base of this. So x is going to equal log of 5, log base 10 of 5 over log base 10 of 2. And now, once we get to our handy calculator, let's go back to my calculator and see what we get. So we're going to do, let's use our division function. So in the numerator, we're going to have our log of base 10 of 5 over log, where's my log? Here it is. Log of base 10 of 2. Oops, of 2. And when I calculate this whole thing, I get 2.32193. So we'll just say 3.32, I'm sorry, 2.32. And I'm also, while I'm at it, I might as well make this proper. I'm going to say this is approximately, because I'm rounding, I need to say, let's just make this all nice and neat, that x is approximately 2.32. It's not exactly, because I'm rounding, so it's got to be approximately 2.32. So that's change of base formula. That's kind of how you use change of base with a couple of different types of problems. Good luck, and I'll talk to you in the next video.